So the last speaker of this session is going to be Meghana, and she's going to be talking about cool application or form of BDDs. With that, hopefully.
Yeah.
Yes. Okay. Make sure
Yes. Hi everyone. My name is Meghana. I'm from UT Austin, and I work with Swarat, Chaudhuri, and Tom Reps. I'm going to talk about weighted context-free language ordered binary decision diagrams. So what is this decision diagrams? It's a hierarchical data structure that can represent enormous sets, vectors, or matrices very compactly. What do I mean by this? In the best case, an OFN data structure, size data structure, can represent a set with 2 power n elements efficiently. So that is, you get a double exponential compression using this. So traditionally, BDDs have been used to represent sets very efficiently. They give exponential compression in the best case. However, they are not hierarchical, and they do not have any weights. That is, they do not have weights across the structure. The value of the function is only at the leaves of the decision diagram. There's this another data structure called CFLOBDDs, which gives double exponential compression and is good for efficiently representing large sets. But what if you have this a function where you have large output value set? In that case, an unweighted structure does not really help, and a weighted structure where you have weights along the structure will really help. And this is work on weighted binary decision diagrams. I'll talk about this in the talk. We're going to talk about weighted CFLOBDDs, which achieves the best of both the worlds. That is, it's good for representing large structures, and it's also good in case where you have large output set. So we use this to represent vectors and matrices, large vectors and matrices efficiently. And this was particularly useful in this case of quantum simulation, where we observed that it really gives best of both the worlds. On these quantum benchmarks, weighted CFLOBDDs perform as well as weighted BDDs and CFLOBDDs. So we're going to talk about weighted BDDs, then weighted CFLOBDDs, and then the application to quantum simulation. So let us take a look at this function of a Harman matrix. It's a matrix over 4 variables, x0 and x1, which represent the row variables, y0, y1 representing column variables. The right-hand side shows the decision tree representation for this function. You have 4 variables. These are called plies, and you have decisions corresponding to it. The values of this function are at the terminal leaves. And at every decision node, you have a 0 decision or 1 decision, 0 corresponding to the left-hand side decision, and 1 to the right-hand side. Now, for one particular value of this function, the assignment would look like x0 equal to 1, y0 equal to 1, x1 equal to 1, and y0 equal to 0. You would traverse the path in this tree. You take the 1, 1, 1, 1, 0, and you end up with -1, which is the value of this function for this assignment. This is the decision tree. It's a standard decision tree. When you go to a weighted decision tree, notice that you still have this decision tree where you have 4 variables. But the leaves, the terminal leaves are always 1 and 0. They do not correspond to the values of the function. You have decisions as similar to what we have seen before, but along with decisions, along with decisions, you see the red highlighted numbers. They are the weights that correspond to the decisions that you're taking. And this will help you get the value of the function for that assignment. Let's see how that is done. For this assignment of 1, 1, 1, 0, you start with the function at the top of the tree. You take the corresponding decisions 1, 1, 1, and 0. But as you go along the tree, you compose the values, red highlighted values here. In this case, the composition is the multiplication operation. So you would do 1 into 1 into -1 into 1 into 1 into 1, and you end up with -1. And this is the value of this function for this assignment. So now that we are seeing weighted decision trees, if you notice, these purple highlighted subtrees are all similar, and they can be merged. You do not have to use different representations for the same thing. So you can restructure the edges to have one common subtree representation. You can do this at every level, and thereby you have a much more compressed representation. As you can notice, there's this decision nodes that point to the same next decision node, and you can remove them as well, and you have a weighted binary decision diagram representation. This is a very efficient representation. It's more compact than the decision tree representation. In the best case, you have an exponential compression, and you're also guaranteed canonicity. That is, for a given variable ordering, you have one unique representation of the function. This is helpful because you want to do efficient equality testing when you're actually testing between if two functions are equal or not. Either also computationally efficient, that is, the algorithms run in polynomial time in the size of the input weighted BDDs. These are some good properties about weighted BDDs. And we want to see how we can move from weighted BDDs to weighted CFLOBDDs. So let's take this function again and the weighted BDD representation. Remember, we removed those two unnecessary nodes. Let's add them back. So you have this weighted BDD representation. Let's take a look at this x0 function. It's a split node. That is, you have two different nodes when you take 0 decision or 1 decision. Let's take this node and add a circle around it. These circles, we're going to call them groupings. Let's do this for y0, x1, and y1 again. And along with this, now we're going to add hierarchy. What do I mean? By this, you add another grouping. These are the level 0 nodes. These are the level 0 groupings. Add a level 1 grouping and extend these edges so that it still represents the same function. You're going to, again, traverse the path in the same way, but you're just adding some sort of hierarchy. Add another level of hierarchy, and just extend the edges as shown here. Now, this is a uncompressed weighted CFLOBDD. We'll see what's special about it. So if you take a look at this, the bottom half of the structure is similar to the top of the structure. And you can, as we have seen in case of moving from weighted decision trees to weighted BDDs, we have compressed structures, right? We're going to reuse only one of these groupings, and we're going to restructure our edges. So let's remove this grouping. Let's restructure this edge to use only the first one. This way, you have a much more compressed representation. You have only, for one particular subfunction, you're using only one representation in memory. So these weighted CFLOBDDs are hierarchical weighted decision diagrams. They follow two principles. One is the matched path principle. If you notice here, you do not, though there are a lot of edges here, you do not run into cycles, because if you enter through a solid edge, you always leave through a solid edge. And if you enter this grouping through a dotted edge, you always leave through a dotted edge. This way, it follows this matched path principle, and you never run into cycles, and all the assignments are represented by the structure. It also follows this contextual interpretation principle. That is, if you notice, the decisions are always taken at the level 0 nodes. And there are weights corresponding to these edges. But these edges are not corresponding to any particular variable, as we have seen in case of weighted BDDs. The variable that you're reading depends on the context when you're reading the assignment. And this way, you can actually reuse substructures without assigning any variables to it. So for this example of, as we have seen, 1, 1, 1, 0, which leads to -1, you start at the top grouping, take the path that follows, take the decision of 1, take the path, you end up with now y equal to 0, y equal to 1 decision, follow the path, and just take the path from level 2 to level 1 to level 0, and then come back, and then you end up with at the terminal value. Now compose all the red highlighted values along this path, as we have done in case of weighted BDDs or weighted decision trees, and you'll end up with -1. So all the assignments are now encoded in the structure. So why is it called weighted context-free language binary decision diagrams? Because this follows a matched path grammar. It's a balanced parenthesis grammar where the edge has a weight. Though it's a regular grammar, because it has this balanced parenthesis, it's called context-free language binary decision diagrams. So when we are moving from weighted BDDs to weighted CFLOBDDs, we are adding hierarchy with this procedure call mechanism. What do I mean by procedure call mechanism? Let's consider this as a procedure, which is being called from two different call sites, and depending on the call site, you are returning to a different point in the original column. So this idea of procedure calls is giving you savings, and when you add this at every level, it gives savings on savings on savings, and thereby you have a much more compressed representation. So if you see the x0, y0, part of the weighted BDD is represented by this blue highlight structure through the solid purple edges, and the green structure corresponding to the x1, y1 is now represented by the same structure, but through the dotted edges. What is weighted CFLOBDD? It's a hierarchical structure. So at every level, you have groupings. At level 0, you have the decisions. As you can see, the fork node and a don't care node. And you have a weight associated to every decision that you take. And at every other level, you have your grouping is divided into 2 parts. One is the A connection and the B connections. It's a bit of terminology, but basically you're moving from level I to I-1 and returning from I-1 to I. And this way you're introducing hierarchy and thereby having compressing substructures. You add some more structure invariants to make it canonical to ensure that you have only one unique representation for a function. So weighted BDDs are read-once branching programs. Weighted CFLOBDDs are acyclic programs with non-recursive procedure calls. The key benefit is that weighted BDDs get their compression from sharing subtags. Weighted CFLOBDDs get their compression from sharing middle of a DAG. So in the best case, you have one grouping at every level, and 2 power 6 variable function is represented by 6 groupings only. So in the best case, you have a double exponential compression over decision tree. And a exponential compression of weighted BDDs. They're canonical, and they're also computationally efficient. So is there an exponential gap? Let's take a look at this function of a population function over n-bit variables set. It is 2 power the number of ones in a binary representation of x. So the left-hand side shows the weighted BDD representation for this function, where for every decision, you have 1 as the weight for the 0th decision and 2 as the weight for the 1 decision. As you can notice already that there's a lot of similarity. There's a lot of structure in the weighted BDD representation. And you can use hierarchy, as I've shown before, to end up with this weighted CFLOBDD representation for the same function. So if in this case, there are 4 variables and you end up with 4 nodes in weighted BDD, and weighted CFLOBDD, you end up with 3 levels. As the size increases, as n increases, you'll have 1 node for every decision in case of weighted BDD, so it would be a size O of n. In case of weighted CFLOBDD, it's O of log n. Thereby, you have exponential compression with respect to weighted BDDs. What about CFLOBDDs? They're also hierarchical, but as we have discussed, they do not have weights along the structure. They only have weights at the leaves. And if you have this function, which has a range of n different values, so 2 power I to 2 power 2 power n, 2 power 0 to 2 power 2 power n, you have n output values, and therefore the size of the structure is at least O of n. So you have weighted CFLOBDDs, which was O of log n, and so it's exponentially succinct than CFLOBDDs as well. So we have seen how weighted CFLOBDDs are better than weighted BDDs and CFLOBDDs. What about the algorithms that you run on weighted CFLOBDDs? How do you do those? So in a typical divide and conquer approach, which is used in weighted BDDs, you have 2 problems of half the size. But in case of weighted CFLOBDDs, you'll have gamma problems with half the number of variables, because you're dividing in the number of variables and not half the number of the output values. So at every connection, as I said, you had an A connection and B connection. For any algorithm that you want to design using weighted CFLOBDDs, you would first operate on the A connection groupings. You will compute some symbolic information which will tell you what to do with the B connection groupings. And this way, you will propagate this information. You'll also note that you'll have to use the weights at the decision 0 levels in some appropriate way according to the function that you want to represent. So if you want to do matrix multiplication, you'll compute one kind of symbolic execution. If you want to do a concatenation or a function addition operation, you'll use another kind of symbolic information. But you'll have to accumulate the weights and assign appropriately. So these are the, okay, so far we have seen what weighted CFLOBDDs are. Now we'll see what is its application. So weighted CFLOBDDs, they can scale to much larger problem sizes because of this compressed representation. There can also handle problems with large number of output values. However, they have some extra structural constraints that you have to add. As I was saying, you have to have the A connection and B connections and appropriately have the edges. Even the level 0 groupings have to appropriately be assigned the values so that you have a unique representation. but do we recoup these overheads? In case of quantum simulation, we see that we do. So if you take the number of qubits that you can scale to, we can see that weighted CFLOBDDs perform as well as CFLOBDDs and weighted BDDs for these set of benchmarks. If you want to look at the performance specifically for this, let's say this benchmark of GSZ, if you take a look at the dark blue line, the dark green line, weighted CFLOBDDs perform as well as CFLOBDDs, and they perform much better than weighted BDDs in this case, in terms of both time and memory. For another function of US gesture, they perform better than CFLOBDDs and weighted BDDs. We notice that in case of QFT, where the output value structure has a lot of values, you notice that weighted CFLOBDDs perform much better than CFLOBDDs, and they perform as well as weighted BDDs, though in some cases, the number of nodes are slightly different. So I also note that this is all on log scale. So to conclude, weighted CFLOBDDs give exponential compression over weighted BDDs and CFLOBDDs, where weighted BDDs get their compression from sharing DAGs, sub-DAGs. You get weighted CFLOBDDs get the compression from sharing middle of a DAG. And adding this extra weights to the structure gives you ability to scale to problems where you have large output size. And we see this in case of quantum simulation, where you're able to scale to much larger number of qubits. Thank you.
Thank you for the nice talk and the nice diagrams. So I was wondering, so besides quantum simulation, have you tried like other applications of this variant of BDDs, like say in like model checking or something?
Yes. So we did try them. In some cases they do scale, but in some cases they don't, and that is because of this extra structure that this hierarchy is introducing. So one idea is, as you can see, there is this level I goes to I-1 at A connection, B connection. Maybe you can relax that grammar mash balance parenthesis grammar, and this slightly different grammar will help you scale better. And I think that is what we are focusing on right now in the future steps. So we did try, did not scale on many of the benchmarks as well as the scale in case of quantum simulation, but we hope that our next work can help us scale the scale.
There are some programs here where you get like much better compression.
Sorry.
Yeah. Oh, sorry. So there are some like circuits where you get much better compression than other ones. Is there like some intuition for what kind of structure is in the circuit that gives you better compression? Or
yes. So there. Okay. With respect to weighted BDDs, you get for these structures you have much better compression. That's because in many of these algorithms, you have, let's say you have n qubits, and you apply something like a Hadamard gate over all the n qubits. If in those cases, this hierarchy helps, because you already have a nice structure, this hierarchy helps you give much more compression of the substructures, which is not possible otherwise. So that's why it scales to much better numbers in case of this. In case of QFT, it scales better than CFLOBDDs by 128x. That's because you have a large number of output values in QFT. And this weights along the structure is helping you give that compression. Yeah.
Yeah. Thanks for the inspiring talk. So something critical for BDDs is the ordering of variables.
Yeah.
So I guess it's still critical for your approach.
Yes.
But isn't there a new dimension of problem how to split this into the several dimensions? So I'm not sure whether dimension was the right term, but you have certain partition, right? Doesn't this complicate the process of finding a good variable order?
So we've used one variable ordering. We mainly dealt with matrices. So an interleaved variable ordering of row and column variables was the ordering that we used. So when there are two parameters here, 2 degrees of freedom, if you say. One is the variable ordering. The other is the grammar. In this case, the grammar is fixed. That is, at every level, L, you always divide it by half the variables. So L minus 1. So first half variables go to the first A connection, L minus 1. The second half of the variables go to the B connection, another L minus 1 groupings. So it's the variable ordering is similar. The variable ordering problem is similar to that of BDDs. But if you want to, as I was mentioning, if you want to relax the structure a bit and want to introduce a different kind of ordering where you have 3 sections saying 1/3 of the variables, 1/3 of the variables, and 1/3 of the variables, that introduces another level of challenge. I think that's something to explore that I think hopefully we'll do it.
Thank you.
Yeah. Thank you.